Welcome to another Mathologer video. Recently, while browsing maths on the web and working on a hardcore video, I got sidetracked by a very puzzling animation. Have a look. There are 12 points performing a strange dance. In certain groups of 3, the points are waltzing in equilateral triangles. At the same time, in certain groups of 4, they're performing a square dance. And if that's not enough, they're also all tracing out a regular 7-pointed star. Pretty amazing. I had a look around on the web and found a few other incarnations of this dance floating around, always more or less viral and without any explanation of the maths at the core of this dance. Now, I've not been able to establish who originally discovered this little miracle and who created this animation. Please tell me if you know. Would be nice to give proper credit. This mathematical miracle was definitely new to me. However, it reminded me of some pretty mathematics that I was very familiar with, and it did not take me very long to make sense of what is going on here. So, let me take this thing apart for you. A great one for the festive season with that Christmas star in the middle. And it also meshes in very nicely with a little paradox that I always wanted to cover in a video. Anyway, some very nice visual maths ahead. Enjoy! So when you have a close look, you'll notice that all points are traveling in the counterclockwise direction around the star like this. Okay, now let's have a look at the equilateral triangles. Bit of a rolling action going on there, don't you think? Points moving around on straight lines and in circles at the same time. Sounds familiar? Well, it should, if you are a regular here on this channel. Remember the video on the Nothing Grinder or the one on epicycles and Fourier series and a nice spirograph math at the core of these videos. Here's a quick reminder. If a circle rolls inside a circle of twice the size, then any point on the perimeter of the small circle traces out a diameter of the larger circle. Super pretty and super surprising. Then, if you trace the paths of a couple of points on the perimeter of the circle, as it is rolling, you get this. There, rolling and rolling, but at the same time moving along straight lines. There, one straight line, a second straight line, and lots of other straight lines. Super pretty. That's the animation I showed you in the video on the Nothing Grinder. Intriguing and really very reminiscent of what we're dealing with in our mystery animation. And I already mentioned the spirograph toy. Well, when you go to the Wikipedia entry on spirographs, one of the first things you see is another very nice animation. Neat, a spirograph can make a 5-pointed star. Mathematically speaking, the curves you get by tracing a point on a small circle that is rolling inside a larger circle are called hypertrochoids. Just in case you don't own a spirograph, there's a pile of apps floating around on the web that allow you to play with these curves. I also put a little Mathematica app together, which I've used to make most of the animations in the rest of this video. Now, in essence, there are 2 things you can play with in the setup. You can vary the radius of the rolling circle, and you can vary the distance of the traced orange point from the center of the rolling circle. Let's first grow the radius of the rolling circle a little bit. Then the traced curve becomes a 7-pointed star. Okay, that looks more like a flower with 7 petals than a star. But we can turn the weed into a star by increasing the distance of the traced point from the center of the rolling circle. There. Great. Just what we want. Well, almost. Unlike in our mystery animation at the very beginning, this star does not consist of straight line segments, right? Well, actually, on close inspection of the mystery animation, it becomes clear that whoever put it together cheated a little bit by replacing a somewhat curved star, like the one over there, by a star consisting of straight line segments. There, have a close look. As you can see, not all the dancing points are centered on the lines. Sneaky. Anyway, not a big deal. Our spirograph star is definitely starry enough for me. Okay, let's roll. Very nice. Okay, now very slowly, so look, let's add another orange point on the rolling circle at that tip of the star. Okay, let's keep rolling. Now it's clear that both orange points will always be moving along the star, right? Pretty magical, isn't it? Let's add another orange point at this tip of the star. Okay, great. Now we have an equilateral triangle, all of whose vertices will always be moving along the star as the gray circle is rolling. Okay, yeah, very pretty. Okay. Okay, that's one of the equilateral triangles that we're chasing. Getting there. Now, let's count the number of times the radius is pointing to the right until it returns to the starting position. Okay, let's go. So there's 1, okay, 2, 3, and 4 times. Great. Now the 4 positions of the disk at which the radius points right are these. Let's roll these disks together. Pretty spectacular, right? Can you see that the 4 orange points always form a square? Nice. Let's add the remaining points to the disks. So 2 more points on each disk, connect corresponding points by 2 more squares. Voila, there are the 3 squares that we've been chasing. Lovely. Let's add the equilateral triangles corresponding to each disk. Okay, there you go. That's how you construct our mystery animation. Now, even if you know how it's done, this animation still looks very magical, doesn't it? But of course, the spirograph can do much more than just draw the 7-pointed star, and so there should be a lot more fun to be had in this respect. For example, there's a second kind of 7-pointed star, this one here. And here is what we get when we replicate the individual steps involved in making our animation. Here's another animation based on a 10-pointed star, which features rotating equilateral triangles.